Hello everybody. On today's episode, I want to show you a little trick about laying out your class member variables in your embedded project that can save you big time when it comes to heap allocations. And this is something, I'm reading this book, High Performance C++, High Performance, and a lot of it's geared towards writing, high performing C++ programs, which I don't think a lot of people are thinking about in the realm of embedded firmware. A lot of people still clinging on to the C ways, and there's just so much in the newer C++ standards, C++ 14, 17, 20 is still not quite hitting embedded platforms, but C++ 17 is on a lot of embedded platforms. And today I want to show you something I learned in this book about laying out your class member variables and how it can be a huge saver when it comes to using memory on the heap. And so for this, I've got this is my little dev board, but this right here is a particle P1 module. So this is we're going to be using the particle platform to show this, but this would apply for any platform that has a C++ compiler because these are just standard things in C++. And so let's just hop right into it. And so I've got a very simple program here that I want to show you. There's not a lot to it. There's less than 45 lines of actual code here. I've got this class at the top, this document class. And this is straight out of the book. And it's got three members. It's got an isCached, which is a bool. It's got a rank, which is a double, and an int ID. And the important thing, and I'm not going to get into the real details of this, but the way that the C++ standard has to deal with class member variables is that they need to be aligned based on the size of each of these. And so depending on their sizes and how the alignment in memory works out, the order that you put these in actually matters a great deal in the resulting size of your object, because the compiler is going to move things around and create padding for you. But if you sort them a certain way, you can optimize and minimize that padding, and it makes your object actually smaller. And so you can see I've got the biggest member in here is going to be this double. Size of a double is going to be, I'm not sure what it is on particle, but it's going to be bigger than int, which is going to be, because particle's 32 bits, that's going to be 4 bytes. And a bool is, I have no idea what a bool is, probably less than 4 bytes. Anyway, the compiler is going to create some padding because of how we've chosen to list our class members here. And I want to show you how that manifests itself. So down here in the setup, all I have is, this is the serial.begin to just, so I can output this stuff over the UART. And I'm going to then print out the size of document by just using the size of, and this will tell us how many bytes of memory we need to store our document class. And then down here in the loop, I'm just going to allocate documents until we run out of heap. Again, a heap is that dynamic, that area of memory that you can dynamically allocate objects while you run. They're not allocated, on the stack when you make function calls or ahead of time like globals or static variables. These are allocated as your program is running. It's often best not to use, as much as you can, stay away from using the heap in embedded applications, because you get into danger zone there. You can get fragmentation and you don't have a lot of heap on these embedded platforms. And so all I'm doing is I'm saying, let's malloc, let's create some memory that's the size of the document. And now you could do this. This is what happens when you new up an object. So if you create a new document by using new document, it's going to allocate that memory and store it. And so just a simple way for us to illustrate this is I'm going to call malloc to create that memory. And then if it gives me the memory, meaning I still have some on the heap, I'm going to print that I've allocated the number of documents, which I'm tracking here. I set it to 0 here, and then I increment it every time I allocate a new one. And then I'm also going to print the amount of, this is a particle call, free memory that's left. And I'm just calling that heap left. And so it's going to allocate a document and then show me how much memory I have left. And as soon as malloc doesn't return, I'm going to just say still allocating is false, and it'll bust us out of that while loop. And so let's see a couple of things we're going to see here. So we're going to see the size of our document object based on how we've laid out our class members and how many of them we can allocate if we run our program like this. So I'm going to go ahead and flash this project to my device. It's giving me a little delay so I can read the output. Okay, serial monitor opened successfully. Oh, we went way off screen there too fast. I need to flush that. I wonder if there's a flush call. Yeah, see, so if I scroll all the way up, I can't get to the top of that. Let's just see if there's a way. Is there like a flush? Serial.flush. Yeah, let's try that and see if we can. Because I put this delay 5 seconds, but it's probably because of how it's executing, it's not flushing the buffer, so we're missing the size. So let's see if that fixes it. Okay. Oh, we got to come all the way back down here. We're gonna miss it. We're gonna miss it. Okay, size of document 24. If you saw that really quick, I'm gonna hit reset so you can see it again. Let's reset it. Okay. All right, it's all the way down here. Oh, we didn't. We had the same problem again. Didn't seem to flush. It said 24 very briefly. I don't want you to have to take my word for it, though. You know what? I got a much better way to solve this problem. This is so dumb. Let's just take it out of the setup here and not be stupid. Okay. Here we go. And let's just say when we're done allocating, let's just print it out down here at the bottom. That way we don't have to race to catch it. Smart. Use your head. All right. Let's come back over here. Oh, we got to scroll back down. Here we go. So we were able to allocate 1,643 objects with our size of our document of 24. So 1643, we'll just take note of that. Maybe we'll just put it as a comment up in here. 1643 with document size 24, just so we don't forget. Okay. All right. And now we're going to make just a very simple change and see what happens. Because these are bigger than our bool, and again, I'm not sure what the size of our bool is. We could do size of and check it, but I'm going to just cut these and put them above. Just like that. So all I did was I just moved double rank and NID above bool is cached. Now the compiler doesn't need to create so much padding for us. It can compress the size of the object. And so I'm not going to change anything else. All I did was rearrange the order of the class members. And this, you know, might not blow your mind if you're a C++ expert, but it blew my mind. And especially, again, this book isn't an embedded book. This is talking about writing high performance C++ in like desktop applications and graphics and games and things like that. But watch what happens when we compile and run this. All right. As soon as it loads, done. 2190. And now the size of our document is only 16 bytes. That is amazing. And so we went from 1643 to, let's get a comment in here, to 2190 with, whoa, document size 16. So just rearranging the members got us that many more documents. I did the math ahead of time, so I don't have to show you the calculator. That's 33% more documents. And now this is a kind of a contrived example of you're not going to just fill up your, heap with classes. However, if you are using dynamically allocated memory, just a simple change of paying attention. And again, the advice this book gives is you want to put the largest variables first, and that limits the padding and allows you to get like this. I mean, this is huge. 33% increase in an embedded system, especially when you're so constrained on memory, is a huge memory performance increase. And so if you're not sure, let's get rid of this for now. I'll just show you how you could do that if you're not familiar. You can always look it up in the documentation, what the sizes of the types are. for particle, but there's some things that are not going to be listed there, like I don't know, like the TCP client and things like that. That's going to have a size associated to it, and you can do I'll show you. You just do serial dot, I print line f, size of int, and then we'll do %d, and all you do is size of int. And so let's just, for our example here, we'll just wrap up with this. We'll say size of int, size of bool, and size of double. Again, this is how you could figure this out if you're not sure. Well, if you don't want to go digging through the documents. And double. Okay. I think that's everything. I don't have anything in loop. Let's just flash that. And as soon as it's done, we'll come back over here, and it should just print those all out for us. Maybe. We get into this weird thing where the buffer's not flushing. Let's hit reset. Come on, particle. It definitely feels stuck. I wonder if it's because I'm in system mode manual. Well, I'm in system mode manual because I don't have credentials stored on there. Let's do system, maybe automatic. Something's not flushing that for whatever reason. Definitely serial print lining. Okay. Now it's going to try and connect to the internet. It's not going to. Okay, there we go. A weird particle. Okay, so size of an int is 4, size of a bool is 1, so just 1 byte, and that's probably because it's just a bit field and you can't be smaller than a byte. And then the size of double is 8. So that's why when we reorder them, we want to have them double, int, bool as last. And now you look at this, 8 plus 4 is 12 plus 1 is 13, but the size is 16. Whoa, size is 16. There's some overhead for the class that's going to be in there. And so from that, we can tell our members are, what I say, 13. That doesn't mean that the class takes up 3 bytes necessarily. There still could be some padding in there. And so that 3 is your padding and overhead. But remember, when we had the order different, when we just swapped the order of these, our size was 24. And so they're only 13 in size. So 24, that's 11 bytes. Again, most of that's padding, as we can tell from this. And so another thing, well, anyway, I'll cut it there. I think you get the idea. Like I said, you can look up this int bool double, but you can't look up things like, what's the size of a TCP client? I think this will work. Let's see. TCP client. All right, last test, and then we'll call it. We'll call the video done after that. This stuff is fun to play with. You don't normally take the time to think about this stuff. Again, unless you're a C++ expert, you might overlook things like this. And again, this can save your bacon. You might think you need a bigger chip with more memory, more flash, but not the case. You just maybe write a little bit more optimized code. And it's still connecting. We'll get there. Okay, size of a TCP client object's 28 bytes. So again, you're not going to find the size of a TCP client in the particle documentation. So if you're going to have, like in one of my in my Puck project, I have a TCP client as a member of a class. That I bet I could go back and reorder some of those things because I wasn't aware of this until, again, I read this book, to get much better memory performance just by rearranging the documents. So I hope that you learned something from that, found it useful. I certainly did, and something that can help you out in your next embedded firmware project.